that's the one that going live, because it says I go live, but it's until I hit it. Okay, now and then I have to mute it on this side, otherwise we hear ourselves in the background all the time.
Okay.
Yeah.
Well, I will trust you to sort out all that stuff, and I'll just try to do
sort it out. Now we're on the live streaming on the other side, and then I'm going to share my screen real quick. Share, and then do you see the?
You're good.
Yeah?
It's
the real thing. I don't know which one I'm looking at.
I know. I mean,
doesn't tell me which one
it
is, so it's okay. And then I usually go with my trusted phone. Where's my phone? Actually, I'll be good if I have a phone. I'll be right back there with my phone. Yeah, it's just the usual phone. Yeah, well, so I think you're done to your duty with the community for the rest of your life, right? You do one of these in your lifetime, and that's it.
Oh, I would never do that. By the end, I enjoyed doing the job, but yes, it's the sort of thing one never does a second time. I think there's one person throughout all of known history who's done it twice. Okay. But no, I'm not that person. I'm happy to let other people have a turn.
All right. So I think it's 3 o'clock now. So I wanted to welcome everybody to the online SPICE and SPIN+X seminars, led by myself in collaboration with Libor Schmekiel, Angela Wittmann here in Mainz, and Karin Eversosite now in Duisburg. And this is coordinated in collaboration with the SPIN+X Collaborative Research Center. There are lots of collaborations, as you see, which is now actually going to be funded for the next 4 years. So this is also hopefully will continue as well. As you all know, this is a webinar format, so you're hearing the speaker, but please write your questions or comments on the chat over the Q&A, or raise your hands and I will promote you to ask your questions after the talk, or if it's important during the talk, or any clarifications. Please look over what the next talks will be. We have one on the 12th of January, 13th of January, 13th of this December. The next one, so next week is not. We have a skip 1 week, but this fixed schedule. It is a pleasure today, actually, to welcome Barry Zink, which is actually a personal friend of mine as well. He's a professor at the University of Denver. He's very high up in altitude, 2 miles up, and then he got his PhD from University of San Diego. And he's been leading particularly a lot of aspects of caloritronics at the mesoscopic level in many of these aspects, and he's been a central figure in that field. He has several awards. He's a PhD Distinguished Visiting Professor at the University of Minnesota, and had an NSF Career Award and the NRC postdoc as well. So with that, I am going to stop sharing and ask you, please, Barry, to share your slide and start whenever you like.
I'm a little rusty with the Zoom stuff, but here it comes, I think. That hopefully looks like a talk to everybody.
Perfect.
Wonderful.
Go ahead.
I'd like to say, so before I get going with the science, I'd just like to thank you, Hira, for the invitation. It's a wonderful opportunity, and I'm looking forward to it. It's not quite as wonderful as I think it was 2015. I got to go and actually give a talk for the SPICE crew right there in the room where you're sitting, far away from here, at Mainz. That was really very lovely, and I certainly look forward to doing that again. But there are some advantages to the virtual world as well, so we'll get going with that. All right, so my plan today is to tell you a little bit about some experiments that my group has been doing over the last few years, where we're using thermal and electrical probes to look at spin effects in a couple of different antiferromagnetic systems. And you'll see one is really something that had been looked at before, and maybe I think deserves a closer examination, sort of a revisitation. And then the other material that we've been working on is a totally new system for us that we've been sort of trying to make sense of for a couple of years now. And so I'll give you some sense of how that's going, which is both exciting because it's new, there's a lot of possibilities, but it's always challenging to try to go into a really new material system. I'll introduce the folks that are in my direct group in a second, but I also have to thank my collaborators who have contributed to the work. That's Shin-Fan, my colleague here at the University of Denver. His some of this work has been collaborative with him, and you'll see that come through. His graduate student Ryan Greening has been the main one who's been helping us out on that collaboration. And then all of the stuff with this new material is a collaboration with my friend and colleague Yayoi Takamura at UC Davis in the materials science department. And her two students, Dane Sasaki and Ishmam Nihal, have helped us out a lot with growing and trying to understand these materials that we're now looking at. All of this work's been funded by the National Science Foundation, so always have to thank them for their support. Of course, the United States National Science Foundation. So here's a picture of, or some mostly bad pictures of my group as it stands at the moment. A lot of this work has mostly been done by the people whose names are sort of in dark red. So that's Matt Natal, who I can never get a decent picture of. Sorry about that, Matt. Sam Blesser. And so they've really done most of the heavy lifting in this particular case. Also, some contributions from Mike Roos, who's a fairly recent PhD graduate from the group, and then Leo Hernandez. Matt and Leo and Sam are all in the process of finishing up and trying to defend their PhD and get jobs. So if anybody's looking for postdocs, you can let me know and I can put you in contact with them. Also, two rather new students are Eric Morris, and one so new I haven't even pinned him down to take a picture yet, and that's Ian Ellis. So we're looking forward to their contributions. A lot of our fabrication is traditionally done at the Center for Integrated Nanotechnologies, which is a campus down in Albuquerque, New Mexico. Most of what I'm going to talk about today is actually done, all the fabrication stuff done in my own lab on materials grown by collaborators. So that's not as big an issue, but I always appreciate those facilities when we need them. All right, brief outline of what I'm gonna go through today. I may skip the little advertisements just to make sure that things run closer to time. Those are just some of our recent papers that will fly by so quickly that you'll have to pause the video later to try to get the references. That's okay. And so we'll start off just making sure everybody's on the same page and talk about spin currents, charge currents, and the conversion between spin and charge currents in a variety of different systems. That will be common information for most folks. So we'll try to just quickly make sure everybody's on the same page. And then the main topic for the first part will be spin to charge conversion in various flavors of chromium, which is an interesting, but sort of maybe not so popular antiferromagnetic metal. So we'll talk about that, and we'll be probing this using what I've put in scare quotes as sort of standard longitudinal spin-Seebeck experiments. And so we'll talk through all of that. A key for us, it turns out, is to be able to do a careful temperature dependence of that spin-Seebeck effect in the chromium. And so that's the next part of that story of chromium, to try to understand whether antiferromagnetism is playing a role by specifically looking at the temperature dependence of the spin-Seebeck effect. And then, assuming I make it through that in some reasonable amount of time, I will show you some of our first results that we're still working to understand well on what I'm calling a low field controllable compensated antiferromagnet. And I'll explain what that means. It's basically an interesting trick you can pull when you look at complex oxide heterostructures. And so I'll explain all that at the end, and then we'll have a conclusion. So there are the brief advertisements. Again, I don't want to say too much. I wrote a very long paper trying to put sort of everything that I thought I understood about how thermal gradients get generated in spintronic systems, with the caveat of looking at essentially DC or DC-like effects. I put it all down on paper. I hope it's something that could be instructive for new people in the field and students. So if that's of interest, I would encourage you to go and look at that. That's some recent papers. Our paper from earlier this year, we actually, it's a sort of a consequence of a lot of the work that we have tried to do in non-local spin transport in nominally insulating systems. That turned it, for us anyway, turned into a very complicated story. So we finally wrote a paper with all of the complications in it. So if you're interested in that, please go and check it out. Okay, so again, just to go back to the very beginning to make sure we all understand what we're talking about, what is charge and spin transport that we're so interested in spintronics. So a charge current is a relatively easy thing to imagine. We talk about them all the time. You've learned about this all the way back in your first experience with physics. If you have an electron, it's obviously got a charge. If you move that electron, then you've got a moving charge. And so if you were to just take imagine drawing a line in the middle of that slide and counting what charge went by as a per unit time, then you would have a charge current, right? But we also know that charge is not the only important fundamental property of the electron. In fact, in spintronics, our favorite one is probably the magnetic moment of the electron. So electrons have spin. So if that same electron started on the left of the screen and moved to the right, and if its spin was pointed up all the time, or if the spin of these electrons as they go is pointed up, then we would say, well, we have a charge current still, but we have also moved angular momentum here. And so that's a coupling of a charge current and this angular momentum flow. The way we really talk about that is to say that it's a spin polarized current. All of the spins are pointing one direction, so we have that polarization. But there's clearly still a charge current here. Now, this is interesting. You can do lots of things with both of these objects, of course. But one simple observation is that it takes work to move those charges in the electric field that's generated by the charge accumulation that you're building up, right? So there's some energy cost to moving these electrons around. And that's, of course, that's a very simple way to think about what is a very, very important issue, is the fact that moving electrons around takes work and causes, and it takes energy. So you could also imagine a really different thing, as long as we're in this sort of PowerPoint world, of taking the spin polarized current that we had at the beginning and then pairing it with one that we've sort of inverted, right? So we'll take a spin up electron on the left, and then we'll just, in PowerPoint land, take a spin down electron and put it on the right. And now we'll just launch them at each other and think about what this might be. So if you play the same game of counting the charge that's moving through the middle of the screen, you now realize that on average, no actual charge is being rearranged. So there's no charge current here anymore. But there still is a separation of angular momentum, or a rearrangement of the angular momentum. So this is one sort of very cartoonish way to imagine what we mean when we say that we have a pure spin current flowing. So here, this is a flow of angular momentum without an accompanying charge current. And if we could have such an object, this is a really useful thing, because now you can imagine sending information in this, encoded in this angular momentum, but without having to do all of the work and waste all of the energy of moving all those electrons around. So it's a very it's potentially really wonderful thing to have, and it would be nice to be able to realize this, right? So now at this point, if we're still in this sort of cartoonish land, if you gave these slides to a first-year physics student, an undergraduate physics student, and said, go make a pure spin current, they would hopefully be confused, because there's no way to take two charges of the same sign and move them in opposite directions in the same chunk of stuff, right? There's just, like, in simple electrodynamics, that is not something that occurs to you how to actually do. But luckily, we have quantum mechanics to pull all sorts of tricks that simple electrodynamics doesn't already know about. And so there are very important and now very well-known ways to generate pure spin currents. One of them is this sort of spin and charge separation that is driven by spin orbit coupling in materials. And so that's quantum mechanics coming in and saying, oh, well, we can take an electron and give it different transverse velocity depending on the nature of its spin, whether it's up or down. And if you then look at the flow of angular momentum in the transverse direction, you realize that that has provided you with a pure spin current. So one manifestation of that physics we can talk about, or we can use the term the spin Hall effect. Of course, there's many different ways to think about essentially the same idea. And that spin Hall effect, we're imagining we have a bulk chunk of a metal with spin orbit coupling. And if we drive a current through that, we're of course launching a flow of electrons. And in this little cartoon, the electrons would be going from right to left through my chunk of this, say, platinum is by far the most common choice. And the transverse velocity that the spin orbit coupling gives to the different spin species makes this up or right spins go up and the left spins go down. And so we've separated those spins by their angular momentum state. But if you step back now and you look at what's happening in that sort of up and down direction, then that looks very much like you've generated a pure spin current flow from bottom to top, or from top to bottom, depending on how you want to define it. And so that's a spin Hall effect, and that's a manifestation of this pure spin current, right? Note, very importantly, this also works in reverse. So if you could get hold of a spin current in a different way, inject it into this material, say from the bottom, then you just have to flip all of the arrows around, and that you end up having all of the charges pile up on one side of the material. So that's called the inverse spin Hall effect, and it's very important because it gives us a way of detecting spin currents that flow into material. All right, so that's pretty basic still. Hopefully everybody is following along with this. And as I said, platinum is by far the most commonly used spin Hall effect material or spin conversion material in all of the experiments sort of done to date, although there's lots of new ideas and exciting stuff of people trying to find other things. And that's basically what we'll talk about when we talk about chromium here in a minute, because in certain circumstances, it actually could be a nice replacement for platinum in some of these experiments. But before we get there, I want to introduce one other effect, and that's basically it's another way to generate pure spin currents, and that's by doing it by applying a thermal gradient. So in this particular case now, we've taken a ferromagnetic insulator, that's this pink thing in the cartoon, and you apply a thermal gradient to it. Now, it's an insulator, so we can't do this thing of moving the charges around anymore, but we do have spin dynamics in the insulator, and so that means we have spin waves, or we can talk about them as magnons if we like. So when we apply a thermal gradient to a system like that, we create an incoherent flow of magnons that are driven along by this thermal gradient. Those magnons are also carrying spin information. They're carrying angular momentum, and so they represent a spin current as well. So this now spin current in this ferromagnetic insulator is launched in the material. It's there. Now you just need to measure it. The typical way to measure it in this experiment that is called the spin-Seebeck effect, or specifically the longitudinal spin-Seebeck effect, is to then use that inverse spin Hall effect that I mentioned as our way of converting that pure spin current into a charge voltage that we can actually measure with a voltmeter. So that's what's happening here. We're thermally launching a flow of magnons that are a spin current at this interface. As they hit the interface, the inverse spin Hall effect converts that spin current that hits the in this case maybe platinum into a charge current that we can measure. And so this is an important experiment now, and it allows you to both, as I will talk about in our experiments here in a minute, probe the spin charge conversion properties of different metals that you stick on top of, say, a relatively boring ferromagnetic insulator, if you want to think about it that way. You can also use it to study novel magnetic properties in the magnetic side of things, if you have an understanding of what's going on. So this is a powerful tool that's been exciting to watch develop. And I'll tell you about some experiments on this here in a minute. But before we get there, even if someone had never heard of the spin Hall effect, like pick some accomplished experimental physicist out of the 1930s, and show them this cartoon, they might recognize it, because this might be the way that they had come had been accustomed to thinking of another important effect in ferromagnets, which is the anomalous Hall effect. So here what we have in a metallic ferromagnet, we have a spin polarized sea of electrons. So already we don't have the average numbers of spin up and spin electrons canceling each other out or being, you know, on average, no spin polarization. We've tipped this toward having some polarization of the spins, which means that now if you drive a current through this thing, the same thing happens. You still can have spin orbit coupling. You still have this sort of transverse flow of the up and down electrons, but the now that we have this imbalance between the ones going up and going left. So that means now we still get a spin current, but we also get a charge current because we had interrupted this balance between the two. And that charge current is very important, has been known for centuries, well, something more than a century. That's the anomalous Hall effect. So one thing that maybe wasn't really realized at that time, certainly wasn't realized until the, you know, in the sort of teens, is that this means that in a metallic ferromagnet, if you drive a spin current into it, should also do the inverse spin Hall effect, right? It will also act as a detector of that spin current for you, basically. So I'm just citing one paper. There are many other ones. Like I should go out and dig in and expand this list so I don't offend people. But in any case, the inverse spin Hall effect in ferromagnetic metals is certainly an important thing. This sort of begs the question, as lots of us are now interested in antiferromagnets, is what about the inverse spin Hall effect in metallic antiferromagnets? And it turns out that's been looked at a little bit too. And so I'm giving the example of chromium because that's what I'm going to talk about here in a minute. So this is an experiment on the left, the first experiment I was aware of anyway, looking at the inverse spin Hall effect in chromium. And again, using that spin-Seebeck experiment that I just described. So there's a thermal gradient applied to a YIG, a ferromagnetic YIG slab, on top of which a chromium thin film was deposited, and then you measure the voltage that's generated by that thermal gradient. And so here you can see this is the signal you expect when you flip the magnetic field. That the magnetization vector is reorienting in the YIG and changing the polarity of the signal. This is all exactly what you expect from the spin-Seebeck effect. The sign is opposite from platinum, which turns out to be a nice, an important thing for many experiments, and so that's what that's about. Here they also looked at the temperature dependence, and it was the specific reason they were doing this is to try to sort out whether anything interesting happens at the bulk nail temperature of chromium, which is around 300, 305 Kelvin. This is work from Chai-Ling Shen's group. I didn't mention he's a good friend, and they didn't see anything happening around this 300 Kelvin sort of temperature range, and so they said, well, this effect, while it's important and should be understood, they said was independent of the antiferromagnetism in the chromium. So recently, some other people have been looking at chromium again, including us. I'll show you our data in a second, but this is an archive paper. I haven't checked to see if this is by now published, and it very well may be, but this is a slightly different experiment. I'm not going to have time to explain, but again, in the inverse spin Hall effect, they do see something different happening with temperature that is hinting that maybe the antiferromagnetism in chromium is playing a role, and that will be the theme of what I'm about to tell you. So I don't need to. I sort of jumped right into antiferromagnetic spintronics without even saying why it's important. I think for this crowd, that's probably doesn't require an awful lot of motivation, but I'll just sort of highlight there's lots of interesting work going on in antiferromagnetic spintronics right now. I think there's fascinating stuff and really interesting possibilities. Of course, the main payoff for this is that those spin dynamics in the antiferromagnets can be much higher frequencies, which can lead to one would hope much faster propagation of information in antiferromagnets. So that's very attractive. Antiferromagnetics also don't have things like stray fields spitting out of tiny elements of the antiferromagnet. So that can be attractive if you're trying to keep, say, two memory elements from not interacting with each other badly in some tiny circuit smashed down in the core of some CPU or something. But there's also a challenge when we're trying to understand what's happening with the antiferromagnets that comes with from the same exact source, right? there's no stray field, so we have trouble understanding what's happening inside of the magnet very often. And so we have to work a lot harder to try to understand what's going on. And in fact, in lots of these experiments, there's some of these done at Mainz and with people, part of SPICE, of course, or SPIN+X. I get all the names a little bit confused, but to figure out what's going on, you often, when you're working with an antiferromagnet, have to rig some tiny moment into it so that you have something to grab a hold on of with an external field, so that you can change the system so that you can understand what's going on. So I say that because at the end I will talk about maybe a different idea of how to achieve that sort of control of an antiferromagnet. Okay, so we've been interested in understanding this sort of spin flow in what's called a non-local spin geometry. I'm not going to talk about this in great detail today, but I'm just sort of by way of the history of how we started looking at chromium. What we really wanted to do was to have an easily produced spin Hall material that would have the negative spin Hall angle compared to platinum, so that we could help understand what's really spin and what's coming from a bunch of other basically charge-driven effects in these sorts of experiments, and help understand that by putting both those spin detectors on the exact same chunk of material, excite them with the same original spin current, and then see the magnon flow have opposite signs on the two different detectors. This was sort of my dream of how we could try to do this and to kind of simplify or clarify the results that we were getting out. And so we started working on thermally evaporated chromium for this reason, because it's cheap, it's very easy to produce in e-beam lithography via liftoff. You get nice sharp features and all that kind of thing. And so it seemed like an easy thing to try to check just to see if it worked. Sort of expected that it would at least give a signal because of the work that had already been done on sputtered chromium. And so we went off down this road to try to figure out whether thermally evaporated chromium thin films displayed spin charge conversion. So we did a very, very standard manifestation of the longitudinal spin Seebeck effect. This is, so we thermally evaporated chromium in a bunch of different thicknesses onto polycrystalline YIG slabs. We smashed them between copper blocks with Peltier elements, applied a thermal gradient and measured the voltages. This was all done in my colleague Shin-Fan's lab. He does these sort of standard spin Seebeck experiments for various things much more frequently than I, we hadn't really done them. And so we were working with him. It was great. So here's the first signals that we get. We can just comparing the raw voltage signal for a 10 nanometer thick chromium film and a 10 nanometer thick platinum film. In this case, it's an evaporated chromium film and then a sputtered platinum film. And you see, quite robust signals coming out of the chromium, which is great. But we got to dig into this a little bit more to understand what's happening. And so the first thing that you think, well, chromium is going to have a pretty bad electrical conductivity compared to platinum. This is what you normally would expect. This is the data for our actual films, several of them, or two of them here. So 6 nanometer chromium and then 10 nanometers of chromium, both this evaporated stuff. What you notice is that the resistivity is really very high. So part of what is happening in these large spin Seebeck signals is certainly just that there's less shunting of the charge that you build up with the inverse spin Seebeck effect, right? So we'll be able to understand that part. But I'll just notice that one of the other common negative spin Hall materials is quite thin tungsten. And so if you just as a point of reference, our chromium has nearly the same resistance as a thin tungsten film does. So it's in that ballpark. So now if we look at this as a function of the thickness in the film, you see something that we were not really expecting. In the sputtered cases that were already published in the literature, you saw sort of a 1/T dependence of the signal as where T is the thickness of the film, which is basically what you expect is, again, the resistance is just dropping because of size effects. And so you're getting more shunting for thicker films, and it's all sort of rather expected. We didn't see that at all. We saw this very different non-monotonic behavior in first in the raw voltage as a function of thickness. You can see there's green triangles are our data. That's compared to then our 10 nanometer thick platinum film. This blue or pink line is the sputtered case there. So you can see this 1/T thing that we didn't get. It doesn't correlate perfectly with the resistivity. It turns out the resistivity of this stuff kind of jumps around all over the place. That's also something that's relatively common with chromium. Chromium's kind of weird in that respect. There's a whole lot of complication there that we won't go into. But the point is that there's no simple explanation of this non-monotonic peak that comes from resistivity. Right? So if you go ahead and you convert all this to the spin charge conversion efficiency, so that's scaling out all the things that are simple, like the geometry, the resistivity, and of course the size of the thermal gradient that you've applied. Then you get this plot here on the right, and you can see that in the case of the evaporated stuff, we see this very different sort of dependence on thickness than was seen in sputtered chromium and other more boring materials. And so we have this sort of weird high spin conversion region where the spin conversion goes up and then it shuts back off again. So this looked very strange to us until we started asking around from other friends who've been working on chromium for longer and looking back into the dim mists of the 90s when people understood maybe more about things like very thin chromium films because of giant magnetoresistance and all this sort of lovely stuff. And you realize that there's lots of phenomenon in chromium thin films where you see these sorts of non-monotonic behaviors with thickness. And the explanation is really that this thickness changes are happening. As they happen, they also change the strain in the film. And the strain, it turns out, changes the nature of the spin density wave antiferromagnetism in the chromium. And so this is already, I think, the first indication that maybe antiferromagnetism is actually playing a role in the spin conversion in chromium. I'll say a little bit more about the actual physics of this here in a bit, but we wanted to do some more experiments to try to understand whether this was really happening. And what we wanted to do really was temperature dependence of the spin-Seebeck effect. And so that's the next thing to talk about. Now, for us, we didn't have a ready-made system that already running to measure the temperature dependence of the spin-Seebeck effect. So my Shinfan's setup is a room temperature thing, enormous blocks of copper in a relatively big bulky magnet. I looked at that, I'm like, well, we got to shrink this whole thing to fit it into our cryostat so that we can actually measure as a function of temperature. And this is a classic thing where I gave those two grad students I mentioned, Sam Blesser and Matt Natal, a bunch of really bad ideas on how to make that happen. And they went off and thought about it and worked on it for a while, and they came up with a much better idea. They actually read some papers in literature, and they said, well, why don't we just do this with local heaters and everything made via e-beam lithography? And I thought, that's a better idea. That's much more our style of stuff. And so this is what you do. They've implemented some already developed techniques to measure what I'm calling the local heating longitudinal spin-Seebeck effect. And so this is relatively simple. You just you make a Hall bar on top of the magnetic material that you're trying to probe. In this case, we're still working on polycrystalline YIG. So we made Hall bars of the various types of chromium, comparing them always to other materials, and you'll see that in the data in a second. But you drive a fairly large DC current through, although not enormous, through the spine of the Hall bar, and then you measure the transverse voltage, and then you pick apart what's happening and what effects are being driven by thermal effects by looking at the symmetries or the expected symmetries of the signal. So heating effects should scale with the current squared, and so basically if you add the result you get from a positive current and a negative current together and then divided by 2, that should give you stuff that is telling you mostly about thermal effects. So that's what we'll call the spin-Seebeck signal in these experiments. Of course, if you then subtract those two, the positive current and then the negative current effect, and then divide by 2, you're looking at things that should be electrically generated, or that could be predominantly electrically generated. And so the typical thing is to call that the spin-Hall magnetoresistance. I think to really, really firmly show that it is actually that physics, you have to be a little more careful. But in any case, those are the electrical effects that you can get, and then you can probe in the same experiments. All right, so this is what we're going to do to try to understand our chromium, because it's very easy to then change the temperature of that system, because it's compatible with all of our cryostats, and away we go. The other thing that's really nice about this is that it actually gives you a much clearer understanding, although still maybe not a perfect understanding, of what the actual thermal gradient you generate in the SPIN-Seebeck experiment is. It turns out that the SPIN-Seebeck experiment is great. Like, you can almost always get a signal when you slap platinum on top of YIG and you get it hot somehow. But to get it quantitatively correct, is a whole other ball of wax, because you really need to determine the actual thermal gradient, and that gets a little bit hard. In our case, when everything is small, there's just this this sort of micron scale wire that is put on top of the platinum. We can measure its actual resistance. The parameters are a little simpler. There's fewer interfaces to deal with. There's some reason, at least for me, maybe it's just because I'm more familiar with these types of issues, but I have more confidence that I know what the thermal gradient is in this experiment. So we measure the resistance of the platinum or the chromium, whichever metal we're using. And we measure it in two different cases of very low current that doesn't cause any heating, and then a somewhat higher current that causes some heating. We calibrate that resistance to use it basically as a thermometer, and then we always know what at least the average temperature of the metal structure is at any time in the experiment. So that's how we're defining the thermal gradient. All the rest of the data that I will show. So here's what happens. This is, again, the raw voltage that comes out of these experiments now. And you can see in blue, we've got the case for the 10 nanometer thick chromium, again, in this sort of high spin conversion region. And we get really pretty significant signals out of this. And again, this is in microvolts here, but that has everything to do with the actual size and how much current we applied, what the actual thermal gradient is here. These are all the same currents for the different materials in this one plot. We'll get it all properly normalized here in just a second. But it's nice that we get a nice, big, easily measurable signal out of the chromium. Right? That's a 25 nanometer thick platinum, which is not, that's probably too thick. You're shorting out the effect you're trying to generate a little bit there. So it's certainly not optimal, but it is a clearly resolvable signal. In a copper film about the same thickness, we don't see any sort of clearly resolvable signal here. That's nice. I'm used to thinking that copper should be my sort of zero reference for this. I know that there's a question now about other types of interesting angular momentum effects in copper. So for the moment, it is providing a zero for these experiments for us anyway. Also, if you rotate the magnetic field, you get the expected symmetries for everything. The signs are all reversed between platinum and chromium. This is all sort of working out well, right? Also, I'll just say, the fact that our chromium here has a quite large resistance is really great for this local spin-Seebeck technique, because the high resistance creates a larger thermal gradient from a given current that you push through it. And so that's part of what's going on, but it also, again, significant spin charge conversion is happening in the chromium at this thickness. Okay, so here's what happens as a function of temperature. Again, comparing the raw voltages on the left, and then we're normalizing it all to give spin conversion efficiency on the right. And so this is kind of a boring way to look at it. Platinum is always better in the spin conversion efficiency, even when it's too thick here. But what we want to do is drill down and look at the chromium and then compare various different types of chromium, right? So let's get right to that. So first, here's that same efficiency plot with just focusing on the chromium. And what we've done here is we've just digitized the data from the Chai-Ling Chen's group's PRB back in 2015, the original sort of inverse spin Hall effect work on the chromium, and normalize it all, and so that we can compare looking at the temperature dependencies of these things. So what we see is that at high temperatures, our data agrees extremely well with the sputtered chromium that was measured by Chai-Ling back several years ago now, but at low temperatures, something different is happening. So we can also look at essentially the DRDT, the change in the resistance as a function of temperature of our chromium strip. This is a common trick when you don't have any other way to try to measure whether there's some magnetic transition happening in a material, right? You can see, well, are there any little blips in this? We see two clearly resolvable blips in this DRDT in our 10 nanometer thick evaporated chromium film. Now, that already maybe seems a little bit strange, because we were talking about transition temperatures of the antiferromagnet before, we were talking about just something around 300 Kelvin. Neither of these blips are at 300 Kelvin either, right? So we need to back up and try to understand what's really happening with chromium at this point. So first, the antiferromagnetic state in chromium is driven by spin density waves. So what we've got is variations in the spin polarization of the Fermi surface itself. That Fermi surface and the variations on it, those spin density waves, can be either what's called commensurate with the lattice or incommensurate with the lattice. So that means that they're happening on different spatial scales, right? So the bulk transition temperature we talk about in chromium when we talk about a 305 Kelvin or a 300 Kelvin transition temperature for antiferromagnetic chromium, that is an incommensurate spin density wave antiferromagnetic transition. But it turns out, even if you have a giant chunk of chromium, you go stick it in and do neutron scattering on it or something, if you strain it, the incommensurate spin density wave collapses into a commensurate spin density wave. That commensurate spin density wave state actually has a higher nail temperature than the unstrained chromium did. So that's 425. Now that's all in bulk. What happens in thin films? A mess of different stuff happens when you go from bulk to thin films. But one thing that can clearly happen is that you can have just classical size effects that scale those temperatures down, right? So, and furthermore, a given film, dependent on the state of the strain that you have, can end up in a mixed state where you have regions where you have incommensurate spin density wave and other regions where you have commensurate spin density waves, right? So at the end of the day, what it all means is that for a given thickness of a given chromium film with whatever strain state you've got, you can have either a commensurate spin density wave, an incommensurate spin density wave, or a mix of the two, and that the nail temperatures of all of those different phases can be shifted depending on the thickness. So that's what we think is happening here, is that these two blips are indicating two different nail temperatures, one corresponding to incommensurate, one corresponding to commensurate spin density waves. They're both shifted well down because of the thickness of the film. And so one is around 200 Kelvin, the other one is around 350-ish Kelvin. Interestingly, what we see in our evaporated chromium is that we get additional spin conversion happening only when we've gone below the 200 Kelvin transition, so that really all of the film, which is in a mixed state, has gone into some quantifiable antiferromagnetic state, right? So I think, again, this is saying that the antiferromagnetism in the chromium seems very likely to actually be playing a role in the spin conversion in the material. Okay, this is the latest update. That was all comparing just to other people's sputtered chromium. We did the exact same experiment that I described with this local spin heating on a sputtered chromium film 2 recently. And you can see, I don't want to get too much into the details, but there are purple dots are our data. The green dots are Chiling's data that I was just using for the original comparison. So very, very good agreement in the temperature dependence of the sputtered chromium films that we're getting in these experiments. So that's another sort of nice confirmation that nothing's too crazy is happening in these experiments for us. One other note, I don't have the data ready, but there's actually in the sputtered chromium that we have, we only see one little blip in the DRDT, not these two, and it's at a higher temperature. So it's, I don't recall exactly whether it's really right at 300 Kelvin, but it's closer to the 300 Kelvin. So for whatever reason, at the same thickness in a sputtered case, the strain state is such that you get a sort of single transition into antiferromagnetism that happens at about the expected transition temperature. Okay, we're now entering the regime of things that most people probably wouldn't give talks about, but I'm a little silly, I suppose. This is some stuff we don't yet understand really well. And the first part of it is just the electrically driven effect in that sputtered chromium that I mentioned. So this, what you could describe this as spin Hall magnetoresistance. But again, I think I would need to have done the sort of all the different characterizations and angle rotations and everything to really talk about this as spin Hall magnetoresistance. I think it probably, maybe at least for the evaporated case, that might be a reasonable thing to say. But in the sputtered chromium, we see this really weird signal that has a very different symmetry than you expect from a magnetoresistance effect. So again, we're still trying to understand this. I'm mostly putting this here in case somebody has seen the exact same thing before and can just explain it to me so I don't have to think about it very hard. But there's already some interesting changes that are happening. Again, the sputtered and the evaporated are very different. And if you notice, the evaporated signal has a sign change from like above this 200 Kelvin temperature to below the 200 Kelvin temperature. So again, this, at least, even though the symmetry of the signals look kind of weird to start off with, there is stuff here that is already sort of corroborating our story of what's happening in these chromium films. More on that to come as we understand it better. I do want to take just a couple minutes and talk about this other system that we're now studying. A few years back, I was watching Yayoi Takamura from UC Davis give a talk. She's a real expert on PLD growth of perovskite oxides and heterostructures of perovskite oxides. She was talking about some beautiful work she'd done where she took a lanthanum strontium manganate film. So that is a interesting colossal magnetoresistance material, but it's a ferromagnetic conductor at the conditions that we're talking about here in terms of the doping and all that. And so she had that material, and then she put a thinner antiferromagnet and a nominally insulating antiferromagnet on the top of that. That's lanthanum strontium ferrite. And in the regime that she was studying with this relatively thin lanthanum strontium ferrite and in the exact doping that she picked, she got something really cool to happen. And it's that, and this is shown in these PEM images taken at the synchrotron at the ALS. You can see that the magnetization vector of the LSMO points in one direction, which is of course controllable with an external magnetic field. But the nail vector of the LSFO on top of it is always arranged at a 90-degree angle to the magnetization of the LSMO. Right? And so that's a particular arrangement of those two magnetic order vectors that she refers to as a spin-flop coupling or a spin-flop arrangement. I know spin-flop gets used for other things too, so sometimes it's confusing for people. But the idea is that these two vectors are quite rigidly coupled to each other, and you therefore can manipulate the antiferromagnetism by applying relatively modest fields to the ferromagnet below it, and move around the nail temperature, or the nail order, which was a very cool idea, it seemed to me. And I started wondering at that time whether there was something we could do with transport experiments to actually probe that antiferromagnetic state, because we have this very easy knob that we can turn, or lever that we can grab and move the nail order around. So we started working on trying to do, originally non-local spin transport experiments on these materials and try to figure out what might happen. So things are kind of hard when you start working with a new thing. One thing that we found out relatively quickly, that the arrangement that had previously been well understood to give this kind of spin flop coupling, this rigid coupling of the nail and the magnetic magnetization vectors, had this very thin LSFO layer. You can just do some AFM. You see all of the real complications of real materials. In this particular case, it involved both some sorts of particulates and things that you often see for pulse laser deposition grown materials. Not always, but they're often in there. You also see just basically missing grains where the LSFO has popped off, and you can see the LSMO just underneath. So already at the fairly beginning of this process, I was thinking probably naively of the LSFO as just an insulator, and the LSMO is this conductor underneath it. Well, you realize that if you put some layer of platinum on top of this thing, your chances are good you're going to encounter one of these missing grains, and all of a sudden you're just putting charge into a ferromagnetic conductor, which brings all sorts of other types of sort of side effects that are going to be difficult to sort out. And in fact, it turns out what we've been fighting for more or less ever since. It turns out or Yayoi has been able with significant work to get rid of those missing grains and to grow somewhat thicker antiferromagnetic layers, so that we're not at least having the problem of a direct contact between our platinum or whatever material we use and the conducting LSMO beneath. Yeah, this is very close to the end.
Okay, you stopped. Can you repeat the last sentence or two? I lost your connection, but my side, I'm not so sure.
Okay, sorry about
the last slide. Yeah, go ahead and repeat it.
This slide, or should I back up one slide?
This slide.
Okay. So the point is just that Yayoi has been able to re-engineer things a little bit so that she gets the same coupling with a somewhat thicker antiferromagnet, which is nice because we can get rid of those missing grains and at least not have a direct connection between the whatever we put on top of this thing and the LSMO underneath. Unfortunately, we still are having trouble where we have conduction and we think we're seeing charge effects in these materials. And I think that's just because it turns out, depending on who you're talking to, we may not always agree on what's an insulator, right? So the complex oxide community often is using insulator as meaning that if I go all the way down to 0 temperature, that I have 0 conductivity. But that doesn't mean that at higher temperatures you can't have fairly significant conductivity. And so, in fact, we've realized that we need to take a step back, and we cannot think of this system as a simple insulator system to manipulate, and that we need to be a little more careful with it. But I'll show you some data which is still showing that there's some exciting potential stuff happening that we think is related to antiferromagnetism. I realize I'm running short on time, and I think I don't have to explain the details of spin Hall magnetoresistance and antiferromagnets. This is something that has been observed, of course. This is sort of just to remind you that often what you see if you're doing these experiments in a transverse sort of geometry, which is what we're going to do, you get the largest sorts of voltages when you have the field applied at a 45-degree angle to the direction of the current that you're defining. So now again, this is well and truly in the case of things most people wouldn't talk about. This is research we're still trying to understand. And so I'm giving my giant, warning that this is ongoing, and we may be we needed to think about all this stuff a little bit more clearly. But I just wanted to show you what happens and what we're seeing so far. So here again, this is the same experiment that I have discussed for the chromium. In this particular case, we're yet to see anything interesting in the thermal side of things, although we haven't turned the driving currents up super high yet. But it seems that zeroth order statement is that the spin Seebeck parts may be kind of boring, but the electrically driven effects are showing some very interesting dependencies on magnetic field. So here, this is rotating the field in the plane of this and measuring that transverse voltage. And you can see this is so platinum on top of this LSMO layer. And you can see these pretty significant, very easily measurable magnetoresistance changes. The largest raw voltages that are coming out at the 45-degree angles, whether it's positive or negative. And there's less happening when the magnetization is aligned with the current or perpendicular to the current. So at the very, from a real bird's eye view, this maybe aligns up with what you might expect from spin Hall magnetoresistance effects. We can look at the temperature dependence. That's basically what this is. And you can see that, again, we have a sort of complicated temperature dependence where the lowest sizes of signals we're seeing somewhat above 300 Kelvin. Below, we see a much larger sort of changes in this resistance signal that we're measuring. And so that, again, that's the question is, how does that correlate with the different magnetization and nail vectors that we expect to be manifested in the sample? Now, we haven't done magnetometry on this exact sample, but I can show you some in just a second on a companion sample, a sort of a similar material that's where we have the nail temperature in the LSFO is near 300 Kelvin. the Curie temperature of the LSMO is right about 350 Kelvin. And so this could be a sign of interesting things happening generated by the antiferromagnet, and maybe not such interesting thing happening in the ferromagnet. But again, one thing that's very clear is we know we have charges flowing around in all this stuff. This LSFO layer is simply not providing a real insulating barrier between the charge. And what that means is that some of the current that we're putting into this platinum is definitely getting into this LSMO layer, because it's quite a bit thicker than either the platinum or the LSFO layer that we have, conducting through that LSMO and then getting back out the platinum and causing some of these signals. We don't know quite yet how much, and that's part of what we're trying to figure out. A first look at how, and a very imperfect one, honestly, to see if we can prove to ourselves that any of these changes have anything to do with spin and have anything to do with the antiferromagnet. We did it by just creating the same sort of Hall bar, except we just removed the channel, the current channel, so that now we're just letting all the current that's flowing in the experiment get down into the LSMO and then come back out. We're still measuring the transverse voltage with the same sort of voltage tap, right? So that's what's shown on the right here. The thing to note, the raw signal voltages are actually much larger. Now that's partly because we're no longer have a direct current path in the platinum across our experiment, so we're not shunting the thing out anymore. So that's why the signals are just larger. But also the thing that's really notable is that the symmetry of the signals has totally changed. So now again, we have the most dramatic things happening sort of at 45-degree angles, but this picture on the right really looks, if you stare at it, like a combination of planar Hall effects, where you get these large 45-degree angle things happening, on top of maybe some background longitudinal magnetoresistance that isn't perfectly canceled off by our geometry. These are the sorts of things you expect from the conducting ferromagnetic material. And so this stuff on the right, most likely dominated by kind of boring understood things. But again, it's got totally different symmetry than the stuff on the left, where we actually still have this platinum spin channel with the possibility of doing interesting spin-related things. So that's promising, but we need to do an awful lot more work to really understand the details of what's happening here. Okay, I want to leave time for questions. There's more crazy things I could show you about how large these magnetoresistance signals get, but again, we're still working to understand this. In this particular sample, we have tied this change in the sort of symmetry of the signal to something happening above the nail temperature compared to below the nail temperature. So it's promising, but again, there's more work we need to do. And I'll leave off, if anybody's interested, I could sort of give a funny tie back to the whole point we started looking at chromium to begin with, but again, I think that's a minor point. So I'll just go ahead and conclude. What I've told you about today, we have these large thickness-dependent spin conversion efficiency in evaporated chromium thin films. That was the beginning of what I think is the story of the antiferromagnetism actually playing a role in spin conversion in chromium thin films. I showed you more evidence of that with the temperature dependence of local heating spin-Seebeck experiments. And I think that's a fairly clear, maybe not utterly conclusive, but I think fairly clear picture that the antiferromagnetism should really be thought of more seriously in chromium for these types of physics. And then finally, I gave you, what amounted to a teaser of work we're trying to do on these exchange-coupled perovskite oxide antiferromagnetic ferromagnetic bilayers, which I think are really interesting, even if they weren't as simple as I thought they would be to start off with. So as always, more data coming soon. Thank you again for the attention. I'm happy to stop and take some questions.
Thanks a lot. This is great. A very good overview of this thermomagnetic effects. So there are things open for questions. Please raise your hand, and I will promote you to let you know. Okay, let me put Tagam is coming up. So let's wait for him to come up to the panel. He's been promoted to panelist. Hopefully he'll come up with panelists. Okay, promote the panelist. Just rejoin. Yeah, it takes a second to rejoin. and then I'll ask my question after that. So Tangan, can you unmute yourself and ask your question?
Hello, can you hear me?
Yeah, we can hear you.
Yes, thank you for your nice talk. I have a very technical questions at page 16. The slide you explained the calibration of the thermal gradient.
Mm-hmm. I'm getting there, I hope.
Maybe, I think it's page 16, maybe a few slides after, yeah.
Yeah, I know where I'm going. I know where to go. It's just whether my computer is slow in getting there. I did it a dumb way, I think.
Yeah, sure.
But I'm getting there. Go ahead and ask your question. It'll be here soon.
Yeah, so you mentioned you measure the longitudinal resistivity of your whole bar as a kind of like a thermometer, but I wonder, isn't it better you just place an actual thermometer on the surface of YIG, because your temperature gradient is penetrating your sample, right? Then basically, I think your bottom part of your sample is having the same temperature as your environment, and your top layer is being heated by the current. So yeah, why don't we just place just a thermometer chip on the surface?
Right.
Yeah.
So keep in mind here, what we're trying to do is only locally generate the thermal gradient. So it is we're not like the typical spin-Seebeck thing. Everything is like utterly planar, large. The film would be covering the entire substrate, and then it's very important to try to have a uniform thermal gradient everywhere. Here in this experiment, you don't have a uniform thermal gradient everywhere. So if I did put a separate thermometer onto the YIG, and in fact, we usually produce many Hall bars on a given YIG substrate. So we do this. Have we actually checked it? I'm not sure. But what I would expect and what I would hope is that at any other place distant from the actual Hall bar that we're heating, that basically we would be measuring the same equilibrium temperature that we would have at the bottom of the substrate, right? So that's sort of the advantage and maybe the challenge in a certain way too of this particular local heating effect. You try to just have the thermal gradient exactly where it can do the physics that you want it to do. So it's only contributing just to what you're actually measuring. Hopefully, that's an excellent question. I hope that
thank you so much. Sorry, but how did you get the actual temperature? So how do you get this conversion plot?
Yeah, so we measure in two different geometries. All of the data that I showed you is measured where we're taking the Hall signal, so we're measuring the transverse voltage in response to the current that's going down the strip, the middle of the Hall bar. Then so to understand the resistance of the structure and then to map that back to temperature, we measure the longitudinal voltage of the structure. That's just to measure the resistance, and then we apply the exact same current that we're going to use in the experiment. That's what the high current is there, and then a much lower current in that experiment. So that basically the idea is that the metal Hall bar is in the same thermal state as it will be in the experiment when we switch the voltage around and do it in the transverse case, so that we know what the average temperature of that metal structure is when we drive a given current through it. And so it's just, we literally measure it in both cases, and then we know what the temperature should be.
Yeah, but I guess if you check like with Wikipedia, you get the normalized resistance, so you need to divide by cross section and length. But in this case, you have a pad which is like in square shape, and your strip is really thin. So how do you
So we convert this. So I know I'm showing resistance here, but I mean, we can convert if we were to discuss the resistivity of the material, we would only ever use the resistivity that we actually measure for this actual film, because it will definitely be different than the resistivity will be different than any other, given chunk of stuff that you would have.
Yeah. Sorry. One last question. Does the size of the contact pads matter for flowing current and measuring voltage?
So as long as the contact pads are large enough to not do strange things like heat up or cause other kinds of weird contact resistances to be important, the size of them shouldn't matter, I don't think.
Okay, yeah.
You do, so the size of the contact pads we make to be big enough to bond to, the size of the strip itself, that is really important, because the amount of heat that you generate will be dependent on the resistance, not the resistivity. So we do choose a strip width that will give a reasonable amount of heat generated for the current that we apply to it. So it's a relatively narrow strip then with nice large pads out at the sides to actually bond to. This cartoon actually is the correct relative sizes, because I believe I made that cartoon by copying the actual lithography file. And then I tilted it on the side.
I see. I think a typical size would be like 800 micrometer times 10 micrometer, is something like that.
Ours are a little narrower than 10 micrometers, I believe, but not exceptionally, not really different than what you said.
Do you remember how large your pads are?
Off the top of my head, I do not, but we're working on this paper right now, and those details are in it. I'm hoping that's submitted like this week or next week. So
okay. Thank you
if
very
you're really
much.
interested on the exact details, feel free to send me an email and I will get you those details.
Thank you so much.
Sure.
Perfect. Is any more questions from the audience? I have one in the perovskite that you showed now. Is the conductivity, is it more semiconducting than for the dope that you have in there, or?
So
because I seen this is very weird magnetic resistance. They are reminiscence of the little magnetic semiconductors that I remember, but I don't know where this one would show up.
So yeah, I mean, the simple answer, the LSMO, yes, is basically a semiconductor at these dopings, but maybe that would be at room temperature. A lot of the really interesting stuff happens at lower temperatures where the electrons are starting to freeze out. One thing that's been frustrating for me about
in terms of not the freeze out, but essentially this definitely the carrier density is not so high, and then that tends to be very sensitive to the directions and isotropies. This looks exactly like gallium manganese arsenide type of weird things that used to happen. Yeah.
And for example, there's work on the planar Hall effect in LSMO, is large effects. Interesting. It does a lot of the same stuff that gallium manganese arsenide does in terms of picking up strange magnetic anisotropies, and so there can be in-plane anisotropies. There's a lot of stuff in the LSMO that can be complicated, which is why I was hoping we could sort of not be so strongly affected by the LSMO, but that is an unfortunate consequence of the reality of things, is that we really are. We are having to sort out what's happening in the LSMO.
I see. Very good. Well, any further questions from the 30 people left? I think that we're all together, 90 people all together between here online and on YouTube. If not, I am going to stop. Hang on a second. The streaming there.